here we go. So here's our first problem. We're going to work the semester as a group. I just want to look at it quickly. It looks like there's a beam. Looks like a pin connection at A, so we'll assume that's a pin, and a roller at B. So how many unknowns do we have in terms of reactions? Three, yeah. 2 at the pin and 1 at the roller. That's good. So we can probably solve this with one free body diagram. Then look at my loading scenario. I've got a point load. That shouldn't be too hard to handle. How are we going to manage this distributed load? Yeah, well, it's usually, if we can, it's best to convert those into a representation with just a concentrated load acting through the centroid. So first thing I'm going to do is I'll draw my free body diagram for the beam. There it is. You like it? Not difficult. Now at the pin, I'm going to replace that with what I'm going to assume is a force in the y direction up and a force in the x direction to the right. Now this is just me, personal preference, but I always assume these forces in your kind of normal Cartesian system. Up's positive, right's positive. That's just the way I do it. You don't have to do it that way, but I would encourage you to be as consistent as possible. So with that as a background, I'm going to also assume that I have a reaction at By acting. I'm going to come back and apply my load. So I know I have right here in the middle a 24 kilonewton load, and it's at 6 meters and 6 meters. And now, as we talked before, I'm going to take this distributed load and replace it because that's a little cumbersome. So I'm going to replace that with a concentrated load. So I like to use the symbol of a double linked on my arrow to indicate that's not really the applied load, that's an equivalent. And this force and that force must be the same. So what's the area under the curve? In general, it's the force. In this case, it's a rectangle, so it's easy. It's just base times height. So 3 meters times 2 kilonewtons per meter is 6 kilonewtons. And the force will act through the centroid of the body, and the centroid of a rectangle is right in the middle. So the middle of 3 would give me the dimensions of 1.5 and 1.5. Now, if I gave you this problem the first exam, for me right here, this is half the problem. If you draw this correctly and you've identified your unknowns, and you've handled the loading scenario, so now you're ready to apply your equation with equilibrium, you've pretty much got half the problem. Okay, so what's the remaining half? Well, the value of the reactions. Now, as we mentioned earlier, I could do a lot of things. I could sum forces in the x direction. Why is that a good place to start? Yeah, there's only one unknown in the x direction, so summing the forces x would be easy to do. What about summing the forces in the y? Should I start there? No, why is that? Well, I got 2. I could write an equation, but it'd be one equation in 2 unknowns. Probably not a good place to start. So back to my original suggestion that if you find a place where 2 of your unknowns are concurrent, for example here at A, at a pin, great place to start. So that's what we'll do. So I'm going to sum moments about A. Now, I always use right-hand rule, which you might remember from statics, which is counterclockwise. So I'm going to sum moments at A using right-hand rule as my sign convention. And here's the powerful statement: the moments are equal to 0. That's equilibrium. So now let's apply that relationship to this problem. So looking about A, what kind of moment does the 24 kilonewton force create about A? Positive or negative? Negative. Everybody see that? So I'll have negative 24 kilonewtons is the force. And what's the distance from A to that line of action? 6 meters. What about the other concentrated equivalent force? Positive or negative moment? Also negative. And that would be 6 kilonewtons is the force. And what's the distance? It looks like 6 plus 6 plus 1.5. What's that? 13.5? So I've taken care of all my knowns. Now what's the unknown? By. And I've assumed it to act up. So what kind of moment is that about A with my sign convention? Positive. And what's the moment arm from A to B? 12. So one equation, one unknown. So solve for By. What do you get? I don't know. Something big. 2, 12, 6, 18. I'm guessing. 18.75. Everybody else get that? Now, it came out positive, so that means that I assume the right direction. Now, that doesn't give me an attaboy or a pat on the back. Hey, you did a great job. You assumed the right direction. It means absolutely nothing. I just assumed the right direction. If I get a negative, big deal. All right? So where did it make any difference when I use By in any subsequent calculation, right? I want to make sure that I keep the sign of whatever this calculation is. So what can I do next? Got two equations left. Which one do you want to use first? Some forces in the X, some forces in the Y. Want to do the Y? Great. I like to assume up for positive, so I'm going to sum forces in the Y direction. And looking at my free body diagram, that's why I don't think it's a good idea to go back and start changing things. If I suddenly if this came out to be negative and I ran over here and changed this direction, then when I read your equation does not match your free body. It looks like to me that you made a mistake. So leave things alone. So now looking at my free body, I've got AY acting up. I've got BY acting up. I've got 24 kilonewtons acting down. And I've got 6 kilonewtons acting down. So plug BY into here. And what do you get for AY? That 7? 11, sorry. And that's also positive, so AY is acting up. Okay, last but not least, we can finish this off by summing forces in the X direction. I'll assume to the right is positive, and the only force I have is AX, so not a difficult equation to solve. AX is 0. And that's it. I know it's a pretty simple problem, especially for the second week of class, but there you go. If you get this on the first exam, will you be happy or sad? I think you would be happy. Extremely happy. So what's the odds of you being extremely happy on the first exam? Not that good. Actually. Well, on the first problem. Maybe later in the test you'll be happy. Any other questions about this? That took me a whopping 8 minutes and 35 seconds to do, even with all the discussion.